After talking about frequency interleaving, let's go to time interleaving. Time interleaving is of little benefit in slowly fading channels, such as for stationary reception, and frequency interleaving offers little to no benefit for narrowband channels that suffer from flat fading. The reason why interleaving is used on OFDM is to attempt to spread the errors out in the bit stream that is presented to the error correction decoder, because when such decoders are presented with a high concentration of errors, the decoder is unable to correct all the bit errors and a burst of uncorrected errors occurs. A similar design of the audio data encoding makes compact discs playback robust. I'd like to then talk about the turbo codes and the LDPC codes. The name turbo code arose from the feedback loop used during normal turbo code decoding, which was analogized to the exhaust feedback used for an engine. In information theory, turbo codes are a class of high-performance forward error correction codes developed around 1990s to 1991, which were the first practical codes to closely approach the channel capacity, a theoretical maximum for the code rate at which reliable communication is still possible given a specific noise level. Turbo codes are finding use in 3G mobile communications and satellite communication, as well as other applications where designers seek to achieve reliable information transfer over bandwidth or latency constrained communication links in the presence of data corrupting noise. Turbo codes are nowadays competing with LDPC codes, which provide similar performance. LDPC codes basically stands for low density parity check code, which is a linear error correcting code, a method of transmitting a message over a noisy transmission channel. An LDPC is constructed using a sparse bipartite graph. LDPC codes are capacity approaching codes, which means that practical constructions exist that allow the noise threshold to be set very close or even arbitrarily close to on the BEC to the theoretical maximum, that is the Shannon limit that we all know, for a symmetric memoryless channel. The noise threshold defines an upper bound for the channel noise up to which the probability of lost information can be made as small as desired. Using iterative belief propagation techniques, LDPC codes can be decoded in time linear to their block length. One of the important applications of OFDM is its integration and usage with MIMO technology. MIMO stands for multiple input, multiple output, and OFDM is, as we all know, is orthogonal frequency division multiplexing. It is the dominant air interface for 4G and 5G broadband wireless communications. It combines multiple input, multiple output technology, which multiplies capacity by transmitting different signals over multiple antennas, and orthogonal frequency division multiplexing, which divides a radio channel into a large number of closely spaced subchannels to provide more reliable communication at high speeds. I'd just like to talk a little more about MIMO OFDM, which is the foundation for most advanced wireless local area network, that is wireless LAN and mobile broadband network standards, because it achieves the greatest spectral efficiency and therefore delivers the highest capacity and data throughput. Greg Rayleigh invented MIMO in 1996 when he showed that different data streams could be transmitted at the same time on the same frequency by taking advantage of the fact that signals transmitted to space bounce off objects such as ground or buildings or any other obstacles and take multiple paths to the receiver. That is, by using multiple antennas and pre-coding the data, different data streams could be sent over different paths. Rayleigh suggested and later proved that the processing required by MIMO at higher speeds would be most manageable using OFDM modulation, because OFDM converts a high-speed data channel into a number of parallel low-speed channels. That was the presentation for orthogonal frequency division. Before leaving, I would like to show some of the codes, MATLAB codes that were implemented for this project. Here we go. This is basically the general OFDM, that is a generation of the signals and OFDM and the reception. As you can see, I've just defined the number of data bits, the number of subcarriers that I would like to use, and the transmitted bits. First will be the generation of a random stream of data. Next will be modulating the data. We'll be using QPSK modulation. As I had said before, you can use any of the modulation schemes. Now, in order to use it with different subcarriers, it is necessary to divide the series data to the parallel streams. Since we are using 4 subcarriers, I'll be dividing the data into 4 bit streams. Next, we'll be using the inverse fast Fourier transform, and we'll be adding a cyclic prefix, which is basically to avoid the intersymbol interference that might encounter. Before transmission, we'll be converting the parallel back to the serial stream, and this is the final data to be transmitted. This is the definition of how the signal will be passed to the channel. At the receiver, the same step goes but in the reverse order, that is removal of the cyclic prefix first, doing FFT, conversion to serial, and demodulation. Let's show you how about the outputs. This is the original data. As you can see, it is just a random bit of stream. This is the mod QPSK data after QPSK modulation. The 4 subcarriers that we are using for the project. This is after doing the IF50 on the subcarriers. This is after adding the cyclic prefix. So as you can see, you just have to link the code to the diagram. It's easy to understand it. This is the orthogonality between the different subcarriers. That is the main function. Name itself is orthogonal frequency division multiplexing. This is the final OFDM signal that has been made and will be transmitted. As you can see, the OFDM signal transmitted and in the channel. So there is some distortion, and this is where the receiver plays a part in getting back or recovering the data. This is the same procedure goes on at the receiver, that is removal of cyclic prefix, FFT, and the received signal. As you can see, the blue lines are the ones that we transmitted, the red ones are the ones that we received. There's some kind of error, right? So this is where the receiver has to be optimized to identify the original data that was transmitted. I'd like to show some other codes which are used. Sorry. This was a one. This is the one for where you use a convolutional encoder. I just found that this is a useful code which can be used to identify the convolution encoding technique, and which will give us a bit error performance of the OFDM. As you can see, if the x-axis represents the energy of the bit. As the energy increases, the probability of getting an error decreases. That's what is required, and that's how it goes. Next is the channel estimation. There are a number of channel estimation techniques which can be implemented, and if I run, I can just show you the comparison of the different channel estimation techniques. It might take some time. This is one of the useful codes that I found relevant. As you can see, it's running the loop. I've defined it from going to 0 to 40. So I can just go through the code. Actually, these are just the defining the number of bits that is required, the formula, that is signal to noise ratio, the sum of the constants defined, and there you go. This is the comparison of the different channel estimation techniques. That is the least square. We talked about the minimum mean square error and theoretical least minimum mean square error. Finally, I've tried to implement one of the techniques uh, of one of the peak to average power ratio technique. Sorry, this is clipping. This is a transmitted signal. This is phase quadrature after using the QPSK modulation. That is I phase and the quadrature phase, I and the Q signals. This is the OM signal that is transmitted. This is the clip signal. This is after the OFDM signal is passed through a high power amplifier. This clip signal. This is the received data. And as you can see, the received data and the received data obtained on clip. So that's it from here, guys. Thanks for watching this video.